Okay, students, this is session number 34 on industrial metallurgy. And let's see what we are offering in this session. This we have already done, but again, for your reference, we will be repeating. And now we'll take another case of a hypoeutectic alloy and discuss its equilibrium cooling. And then the last case of hypoeutectic alloy is the third case, where we'll take an alloy of 30% tin and discuss its equilibrium cooling. So as we have discussed, there are three categories of these alloys. Eutectic alloy, this should have been hypereutectic, and these are hypoeutectic alloys. So in the last session, we discussed hypoeutectic alloys, first category. We took the example of 5% tin alloy. Now we are taking the second case. If a hypoeutectic alloy contains anything between 7 to 19.5% tin. So for your reference, we are considering an alloy which is containing 11% of tin in it. So we take this alloy at a very high temperature. We mark this composition, draw a straight vertical line, and take this alloy at a very high temperature, represented by point L. When it's in the molten state, it has got only one phase in it. The chemical composition of the phase is the same as the chemical composition of the alloy in which it is there. And then we start equilibrium cooling of this alloy. As we cool this alloy under equilibrium conditions, no change takes place in the microstructure till we have reached its liquidus temperature corresponding to point M. At temperature corresponding to point M, that is the liquidus temperature, the first solid phase appears in the microstructure of the material, and this is the chemical composition of that first. The solid phase appears in the form of alpha, because we are in the liquid plus alpha region. And using the tie line Tm, we can find out the chemical composition of this first solid phase that has appeared in the microstructure of the material. The weight over here is just 0.01 weight percentage. The liquid phase has a slightly different composition from where we had started, and still bulk is liquid only with 99.99 weight percentage. As the temperature drops further from point M to now point N, again we are trying to show the microstructure. We have again drawn the tri line. You would show the chemical composition of the solid phase alpha, and we would show the chemical composition of the phase liquid solution. You can clearly see that these critical nuclei now have grown into the form of dendrites. The amount of solid phase has increased from 0.01 to almost now 73.68% at a lower temperature corresponding to point N. Both chemical composition of the liquid solution phase and that of the alpha phase has also changed. As the temperature drops further and we reach point O, this represents the solidus temperature of this alloy, where solidification is just on the verge of getting completed, and you can now see the last traces of the liquid phase in your alloy. Importantly, you must note what is the chemical composition of this last liquid that phase that is being seen in the alloy. For that to know, you will have to draw this tie line OW, and W would give you the chemical composition of the liquid phase, which we have put over here as 49% tin. Now, opposite to this case where first solid had appeared and the weight of solid phase was 0.01%, at the liquidus temperature, at the solidus temperature, we are considering now the weight of the solid phase as 99.99, and the weight of the liquid phase is just 0.01%. With any further drop in temperature, complete solidification will take place. So at any temperature just beyond point O, the solidification would have been complete, and what we realize is that we are lying in a single phase region alpha. So here we are in a single phase region alpha. Because it's a single phase, the chemical composition of this phase would be the same as is the chemical composition of the alloy that we have taken, 11% tin. We keep on cooling this alloy. No change takes place in the microstructure of the alloy till this vertical line crosses against the solvus line. Now this is representing that from this temperature till this temperature, when there was alpha solid solution in the system, what was happening when the temperature was dropping from point TO till point TQ, you can say that alpha solid solution was getting saturated in tin, because alpha solid solution is a solid solution with tin as the solute present in the solvent lead. So somewhere over Q, now this alpha solid solution gets fully saturated in tin, and if the temperature is now dropped, alpha would say that I will not be able to accommodate this 11% of tin that I am accommodating in it. So no sooner the temperature of the material system falls below temperature TQ, you'll see that beta, we have landed up in the alpha plus beta region. And why? Because alpha has started precipitating 10 out of it in the form of beta solid solution. So just below point Q, if you try to see the microstructure on the grain boundaries, this beta solid solution phase starts precipitating. Drawing the tie line, you can find out the chemical composition of this beta solid solution. Weight, because it has just started precipitating over at point Q, we have written its weight as 0.01. But students, as cooling will proceed, because of this solver's line, alpha will not be able to accommodate large amount of tin in it, and continuously will keep on precipitating out. And this tin being precipitated out of alpha will take the form of beta solid solution. The amount of beta will keep on increasing. So where beta here was 0.01%, here it has become now 3.33%. Also the chemical composition of alpha and beta has changed. And please remember, whensoever in the presence of a solid solution, we already had an alpha solid solution over here. If in the presence of a solid solution, if another solid solution is to precipitate, beta starts precipitating, it will always come at the high energy areas, the defects, etc. And here the high energy areas in the grain structure is always the grain boundaries. So you can see that beta phase has deposited itself on the grain boundaries of alpha solid solution. Next, let's talk about another hypoeutectic alloy, category 3, which had in it a tin quantity between 19.5 to 61.9. Now, if we consider this alloy at a very high temperature, suppose just for illustration, we are considering an alloy and a hypoeutectic lead tin alloy, which has about 30% tin in it. 30% tin in it. So again, mark this composition, take the vertical line, take the alloy to a very, very high temperature when it's in a complete molten state. So what we see is that at this temperature corresponding to point L, the 30% tin alloy has got only one phase in it, 100% by weight, 30% liquid solution. We start cooling this alloy and no change occurs in the microstructure of the alloy till we have reached its liquidus temperature corresponding to point M. At point M, this is the microstructure. We have liquid phase in bulk, and we have this first solid phase which appears in the microstructure of the material. To get the chemical composition of this solid phase, please make use of the tie line. As the temperature drops from M to N, we can note that these solid critical nuclei have grown into the form of dendrites. The amount of solid phase alpha has increased from 0.01 to about 41.67%. The chemical composition of both alpha and liquid have now changed. That of the liquid phase is changing along the liquidus line, and that of the solid phase will change along the solidus line with any drop in temperature. When we have reached a temperature corresponding to point O, this is an important temperature and an important observation. As we reach point O, we are reaching a temperature, the eutectic temperature, and we have liquid solution present in the alloy. Importantly, at the eutectic temperature, the eutectic composition, the liquid solution has got eutectic composition. So it is this point, it is this temperature where you will find this maximum amount of alpha that has formed because of simple solidification. So if you look at the microstructure at point O, you see alpha is 75.24 and liquid is 24.76. But importantly, this liquid is of eutectic composition, and moreover, it is present at the eutectic temperature. So as you cool now, and when the system exactly reaches eutectic temperature, this entire 24% liquid undergoes the eutectic reaction via which this entire liquid transforms to alpha and beta. So this alpha and beta which would be formed from liquid would be called eutectic alpha and eutectic beta, and this alpha which was already there would be called pro-eutectic alpha or primary alpha. So just after the eutectic temperature, if you look at the microstructure at point P, the microstructure would be that liquid has transformed into lamellar eutectic alpha and eutectic beta, and this pro-eutectic alpha remains as such. And if you are interested in finding out that